Hi, everyone. So today we have Laura Colmenarejo from where are you now? I forget.
UMass.
Are you in Boston still? UMass. Who's at UMass, who'll be talking to us about chromatic symmetric functions for DICKPATHs and Qrooks theory. Take it away.
Thank you. I'm really happy to talk about this project here. Let's see what you think about it. Let me say that I have prepared what I consider a very slide version of the whole paper, and I hope to give you the sense of why I have done that. So the first thing that I want to do is I want to define some of the words that are on the title. And I want to start also mentioning that this is joint work with Alejandro Morales and Greta Panova, and that I really, really hope that we get the extended abstract is already on arXiv, but I hope to get the full version of the paper this week or the coming week on the arXiv. So just keep an open eye for it. So the first thing I want to talk is about the chromatic symmetric functions. So if I think about this as a mathematical object, the first thing that I have in my mind is that they are going to encode colorings of graphs using monomials. So suppose that I have a graph and I'm going to look at the vertices. As you see here, I have n vertices that are going to be totally ordered. So in particular, like many ways of representing this, I'm just going to be using the numbers 1, 2, all the way up to n for the vertices. But at the same time, I'm also going to use the numbers 1, 2, 3, etc. for a set of colors. And the way that I'm going to encode those the colorings with monomials is using an alphabet. So the color 1 represents the variable x1, color 2, the variable x2, etc. So what Stanley did to go from colorings of graphs into symmetric functions was saying, okay, for each proper coloring that I have of the graph, and I'm going to explain what is proper in a minute, what I'm going to do is I'm going to associate x to the k, where x to the k is just taking, okay, how many vertices are colored with color 1? How many vertices are colored with color 2? And we are going to keep those as the exponents. And as a reminder, proper coloring, what I'm gonna consider here is that if I have two vertices that are linked by an edge, then k of u has to be different than k of v or kappa. So I cannot put two vertices with the same that are linked by an edge with the same color. And if you think about like having like associating to each of the colors one of the variables as something that we could actually permute, then you can see that these are symmetric functions. So let's see if you follow how we construct these polynomials, well, these symmetric functions, with an example. So what I have done here, I'm taking this graph with 5 vertices, and I'm going to take 4 colors. I have denoted them with x1, x2, x3, and x5, and I have different colorings. So if you think about the first one, what I'm keeping here is the numbers associated to the colors. So if you look at x1, this means the orange color. So how many do I have here? I have 2, so I have x1 squared. If I look at x2, which corresponds to the blue one, I only have 1. If you look at x3, which is the pink one, doesn't appear, so I have x3 to the 0, and then x5 squared. Now, if we do the one that is on the right, I can see that I also have.
Where is x4?
There is no x4 because I just choosing 1, 2, 3, and 5.
Okay.
As the variables, I can choose, like I wanted to encode with 4 different colors, but I wanted also to show that doesn't need to be like always consecutive colors. So what I want to show you with this other one is that I could actually get the same monomial with 2 different colorings. So in this case, I'm also going to have x1 squared, x2 to the 1, no x3, and x5 squared. But as you see, you can see that these 2 colorings are actually different. But if I permute the colors, I'm actually getting the same. Now, the one in the bottom, this one has x1, x2, and x3. So I'm gonna have that x1 appears twice, have these two colors. X2 appears one, and x3 appears another 2 times. And then x5 doesn't appear. And just in case you don't remember what is a proper coloring, this one over here shouldn't work because I have 1 and 3 that are linked and they have the same color. So this is actually not taken into account. So when I write my symmetric function over here, among all the terms that I'm gonna have 2 times x1 squared, x2 to the 1, x5 squared, and I'm also gonna have another monomial that is of this form. And by putting just these 3, it means that I'm recording these ones. It could also happen that in these dots over here, I also have other, like this monomial repeated.
Even the top one may be greater than 2.
Yes. Exactly. I'm not claiming that the coefficients for these ones are 2 and 1. Okay. Now, during this talk, we are going to be focusing on some particular set of graphs. Among all the graphs, we are going to be looking at those that are coming from DICKPATH. So a DICKPATH is just a path that goes from the 0, to n. So I have here an example. I'm only going to be allowed to take north and east steps. So I can only go up and to the right. And then the condition that I have is that I don't want to cross this diagonal. And those are I'm gonna call them DICKPATH. And from them, I'm gonna read a graph. The way that I'm gonna read a graph is that the set of vertices are gonna be 1 up to n. So I can put the kind of like split the diagonal into n pieces, and each of them is gonna be, I'm gonna label them 1 up to n. In this case, I have 1 up to 8. And then every time I have, I'm gonna construct the set of edges by setting that if ij is an edge in my vertex in my graph, if I is smaller than j, and this box is below the path. So basically what I'm doing here, I can go like, if I'm looking at 1, I can link 1 and 2 below the path, and I can link 1 and 3 below the path. So I can say that 1 is linked to 2 and to 3. Now, if I look at 2, 2 can go to 3, but you see that I cannot go to 4 below the path. So 2 is linked to 3, and I'm done with that. Now, if I look at 3, 3 can go to 4 and 3 can go to 5. So 3 can go to 4 and 3 can go to 5. And now 4 can only go to 5. So I have this one over here. Now you see that I'm touching the diagonal, which means in the case of the graph that I'm having another component, disconnected component of the graph. And now if I'm looking here, I'm only missing like kind of like this box here, which means that 6 is linked to 7 and 7 to 8. Am I only having this one? So this is the way that I'm gonna associate to a DICKPATH a graph. And later on, we are gonna even restrict even more the set of paths that we're gonna be looking, the DICKPATH. But for now, this should be enough, because what I want to look at is actually a generalization of the chromatic symmetric functions. But let me tell you what is the problem that I'm focusing on. Stanley and Stanbridge conjecture that if I look at the chromatic symmetric functions coming from this DICKPATH, this graph coming from DICKPATH, they are E positive. Now, by E, what I mean here is the elementary basis of the symmetric functions. And by being E positive, what I mean is that all the coefficients that are not 0 are actually all positive when I expand my symmetric functions in terms of the E basis. And if I were to think about like what I really want to solve here, I actually want to have a combinatorial description of the coefficients such that there are no negative signs. So I'm saying that this is my ideal world because we are not gonna get there. Now I want to jump into
Can we ask question?
No.
Okay.
What do you want to know?
You said no. Anyway,
I mean, you asked if you could.
I have many things in my mind and I don't know when to ask them. So first of all, have you considered the Cherchen wax quasi-symmetric function?
That's my next slide.
And have you considered the S positivity?
No, because the reason why we want to go for A positivity is because it's the strongest. So
I understand, but the S positivity is shown in this case. So, yes. But you still understanding the coefficient could be interesting. So for your ideal world, you can push further with sure positivity.
Yes, that's true. But what we have been able to do right now is prove something using Qrooks theory. So kind of like open the door to something or connecting things that were already around.
Yeah.
So we haven't thought about what happens in the sure case.
Okay, thank you. Sorry, I'm like that. I interrupt all the time.
It's not like I don't know you. Feel free to continue.
Go on.
So the Q is chromatic symmetric functions, and the reason why I put symmetric in parentheses here is gonna show up in this slide if you just continue reading. But what Nantel was saying, can we consider a Q generalization? So I usually don't think about the Q analogs as generalizations. I just think about them as refinements. So for me, it's kind of like giving us more information to see if we can do it in smaller pieces. So what Saration and Walks did was actually looking at the chromatic symmetric function and say, okay, I can add a parameter Q in the following way. So now I'm still looking at proper colorings. Now for each of the monomials that I have, I'm gonna associate Q to the to these statistics here. So what I'm counting here is the number of edges such that I'm ordering my vertices. You remember they are totally ordered. So U is smaller than V. And now the color of U is smaller than the color of V. And we are going to do an example, like the example that we had from before again. But I just want to mention, because I put here that the symmetric, so you are not mistaken, that in general, these are quasi-symmetric functions. But for the graphs that are associated to DICKPATH, these are actually symmetric functions. So that's why I'm putting here that these are symmetric, and instead of just putting the general case of having quasi-symmetric functions. So in the example that we had before, now what I'm having here, I'm having the same coding of colors that I have, but now I just have to order them. So I have that 1 is smaller than 2, smaller than 3, smaller than 5. So if we look here, I usually like to go in order. So if I'm looking at this example over here, well, so now I'm looking at this labeling of the colors. So 1 is smaller than 2 and is smaller than 5. So if I were to count here, I will have, like, let me choose this one. This one is giving me an ascent. This one is giving me another one. And now 2 is smaller than 5. So I have another one here and another one here. And now 1 is smaller than 5. So I also have another one here. So actually here, all the edges are counting and adding 1 in the number of ascents. So I have 1, 2, 3, 4, 5. So this is Q to the 5 over here. If I do the other example that I have on the right, now we see that 5 is the largest. So none of these ones are counting. Either is going to count this one. But if I look 2 and 3, the vertices 2 and 3, then I also have that the blue color is larger than the orange. So that one it's not counting. And the same happens with this one. So here I actually have that none of them is counting. So I have Q to the 0, which is just going to be 1. And in the last example here, what I'm going to have now is that 3, the color like pink is larger than the orange, but is also larger than the blue. So this one is not counting. But now the orange one is smaller than all the other ones. So here I'm going to have 1 and 2. So these are counted by Q squared. So if I'm looking at the new way that I have of encoding this, I'm gonna have for these two, you remember that this one was x1 squared, x2, x5 squared. So here now I'm gonna have a 1 plus q to the 5. And this other one is the q squared. So this one is gonna be the x1 squared, x2, x3 squared. Which,
Laura, shouldn't the coefficient be q cubed because the orange is less than the blue as well, from 2 to 3?
oh yes. Thank you.
And there's a question in the question was the same thing in chat. Never mind. Okay.
Yeah, that was the same. Okay, so that is what I'm thinking about, like a refinement using Q analogs means that this number 2 now is, I'm gonna look at it at 1 plus q to the 5. If I put the q equals to 1, then I'm recovering my coefficients here. So what Sarich and Wack's conjecture was that I have the analog for the conjecture from Stanley and Stenbridge. That if I look at these chromatic symmetric functions in the case of the DICKPATH, and I expand them in the E basis, then the coefficients are gonna be polynomials in Q with positive integer coefficients. So I have polynomials in this ring. And I want to talk about a little bit like of what has been done in this case. And for that, I have to restrict a little bit more my set of graphs that I'm considering. So instead of looking at DICKPATH, I'm going to look at what are called abelian DICKPATHs. And the reason why these are called abelian is because there is another role in which this also appears, more related to Heisenberg varieties as one of the references here. And in that case, that is related to some ideal for which being abelian means something more complex that I can explain in the seminar today. But the DICKPATHs that we are considering here are very special, I will say. So what we are doing is that we are going to have like two parameters. So here there is an M and an N. And what I'm doing here, I'm taking M step north steps, and then I'm doing something, and then I'm making sure that the last step are all east. So there is like a prefix beginning and end to the DICKPATH. And there is here a double U lambda, which is going to be encoding the path given by a partition. So here now I have a rectangle that is M times M, and I have a path here. So the way that I'm reading this is that I'm in the complementary shape, I have a partition here. It takes a little bit of time until you get more comfortable of that way of encoding the graph. But what this is basically saying is that for every partition that you have inside a rectangle, you can look at it as a graph associated to it. So to do that, you have your partition, you complete up to having half of the square, and now this is going to be a DICKPATH, this one that I have over here.
But does your partition lambda have to go up to the edge of the
yes
of the M? So in other words, you're saying that the bounce path has 2 steps, or
this one should be like that. Can you repeat your question, Mike?
are you saying that the bounce path of the DICKPATH has 2 steps?
Yes. And your question just made me realize about something.
That might not be true, isn't it? Because do you fix the M and N, or is like are you allow N to be slightly smaller? So like say in this case N equals 4, do you allow the first step past the M line to be a north step?
If I'm allowing this to be like this?
Yeah, exactly.
Yes.
Oh, then it's not quite what Mike said, right? Because the bounce step would pass M, or is Mike referring to something different?
Yeah, she just said lambda is included in n by m, not that it's fully n parts positive.
Yeah,
Right.
but my first question was the lambda forced to touch the M line?
Yeah, but I
And-
think that she
okay.
answered yes, but she means no.
I mean, yes, no, I was thinking about something else. Okay, yeah, no. Like it could be completely inside. It could be just this, even if I'm considering this m times n. But there are some ways on which, like, yeah, we can control those cases. Like if you consider an m times m rectangle and your partition actually fits in a smaller one, then there are ways in which we can control what is happening in the case of the chromatic symmetric function. And now, in this case, I post here like 3 references. The first one is by Cho and Hu, who actually describe what happened in this case, where they gave an expansion in the elementary basis using p tableaus. I also wanted to mention, I put here Harada and Precap, because there is another approach to this problem based on Heisenberg varieties. And they also did some work in this particular case. And then the work that I want to talk about today is the Abreu-Negro, in which they included what is Qrook and Q-hit theory. So I do have a couple of minutes more. So let me talk about, at least at the beginning, of what are the what I understand for Qrook and Q-hit theory. So I'm gonna say that for me, the word rook doesn't mean anything. I know that in chess means something, and for many people, you often, like, initially you think about some moves in chess. For me, when I start working on this, it wasn't meaning anything. So Garcia and Remmel defined the Qrook numbers as a sum of it's gonna be Q to some powers. So the way that I'm gonna define them is I'm gonna have a rook placement. So I'm gonna put K rooks in a partition. So here I have the partition 9, 8, 3, 3, and I have put it 4 rooks. And the condition is that I can have at most 1 rook per row and column, and they cannot touch 1 per row and column. And now these rooks are gonna attack, or they're gonna be cells that are attacked. And I wanna do it in the following way. So I want to do southwest. So if I have a rook, I'm gonna go south. Let me use all the way south. Here I'm passing the partition, but just because I want to make sure that I cancel that. And then I'm going to the west. So I have this one, this one, this one, and this one. And now the other cells that appears here that are not covered, not attacked. In this case, I have these ones and this one over here. Those are the ones that I'm gonna be counting. So what this is telling me is that I have a Q to the 6th. For this particular placement, for this particular P, I have a Q to the 6th. So what I'm gonna be doing, if I want to look at R4 of lambda, I'm gonna be looking at all the possible ways of putting 4 rooks here, do the attacking, and then count the number of boxes that are not covered, and then keep them as a power of Q. And now I want to generalize that to what are considered Q-hit numbers. And there is a reason why instead of giving a very nice combinatorial formula, I'm giving you this other one. So Garcia Remmel defined the Q-hit number to be, I think about this like a change of basis. It's a very complicated one. But here we have the Qrook numbers. And then I have a bunch of other factors over here. And I just want to say that all of them are Q analogs. So in the, this is gonna be the Q analog of the n factorial. And every time that you see something on the slides that is gonna be with the brackets, I'm meaning Q analog. Now, when we were working on this program, we thought that it will be like, we look at the literature, and there were actually different ways of realizing these Q hits using boards. So what I want to do is okay, I have these numbers, and I want to like kind of like what I was doing for the Qrooks. I want to put out like a rook placement on the board, and here the M and N are gonna define my board, and then I'm gonna have a shape, and the K is gonna say how many of them are inside the shape when I'm having N in total. And then I want to do some kind of attack, and then I just want to count the number of boxes that are in non-attacking. So the problem here that we encounter is that there were two versions for the square boards. So when we were looking at the literature, there were different versions that were actually not they were not actually not the same. This was very confusing. So instead of telling that, because I just have 1 more minute, so before stopping, so I will come back after the break. But just I want to say like that we chose one and we went with it, and in the paper we have clarified what are the differences between the two of them, a lot of relations between them, and kind of like put among all the literature that we found that were using the two different versions, which of them were they using. So I will do that after the break. So for the square boards, they gave us a hard time because different papers had different convention on how to do the attacking. And initially we thought like all of them were similar or were like they were equally distributed, which is what happens in the case of the rook placements of the Qrooks. So because in the case of the Qrooks, there are very nice properties when you conjugate and when you consider, there are some properties that are preserved. There are many different ways of doing the attack. So instead of just doing like I did here, I did south and west. If you do north and east, it's gonna be the Qrooks are gonna be the same. Maybe for one particular rook placement, that like they are not the same. That is not gonna be true. Like it's not that I can change and I will always get for the same placement, the same power of cube. But when I look at the sum of all of them, they are equidistributed, so I get the same Qrook number. So we thought that that was the case that was happening for the square versions of the Q hit numbers. And what happened was that it wasn't. And let me show you two of them. So I want to do, I want to do south and east. And in the east, I'm gonna have a cylinder version of it. So let me explain what I mean by that. So every time that I have the Qrooks, the rooks on my place on my board, I'm just gonna go all the way south. So this one, all the way south. And now I'm gonna go all the way to the east, but I'm gonna be facing the partition at some point. So in that case, I'm just gonna stop. So I'm going east, so I'm going to the right. So in this case, I just like, I get up to the point of the partition. In the first one, I'm just getting there. Here, I'm going here. Now, if you look at this one that is outside the shape, then I can continue until I face the partition. So it's actually like, I'm thinking about it as if here I was having, like I was continuing, I'm thinking about a cylinder. Now here I'm just touching this one is gonna eliminate all of this. No, it's gonna go here, and this one is just gonna go there. And if I'm counting, well, let me do the counting. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here I have Q to the 11. Now, this other version, what I want to do, let me take a note, quick note here. I want to do north, and I want to do the west. And the west is the one that is going to have the cylinder. So I'm going all the way north. And now I'm going to the west, which is to the left, and up to the point of touching the partition. So this one will cover all of this. This one will cover all of this. This one, this one, this one, and this one. And here I should only have 4 left. So I have this one, this one, and this one. So here I have a Q to the 4. And as I'm saying in this remark, they actually differ just by a power of Q. And we were able to like figure out which one is the power of Q they differ. But the problem is coming that when you look at the relation, this differentiation, like this power of Q that they differ by, is actually affecting way more than one would expect, especially with some deletion contraction properties. So the one that we decided that was the best one, an hour, was this one over here. And is the one that we are going to be keeping. So we are going to translate it into what happened when I have non-square board. So I have cylindrical, rectangular one. And I do the same. We are doing south and east. And I'm using the cylinder component in the east one. So in this case, so I'm going all the way to the south. And now to the east, up to the point where I touch the partition. So in this case, I have, yes?
I was going to ask a quick question.
Yeah.
Has anyone looked at like other ways of doing this? So like south and west or north and east? Or like what happens in those cases?
So I think that there are some of them, like depending on like, because that's another thing. Some people put the partition on the bottom right.
Yeah,
So,
no, like assuming the same partition. So like the same way of drawing a partition, like you have here. Do we get anything nice if we look at south and west or north and east? Or
I think that there may be 2 of them that are equidistributed, but I'm not sure.
okay.
What we actually tried to do was stick to the one that was working for our computations and try to figure out what was the problem with the other one. And that was
Okay.
all.
That works. Thank you.
So here I have 4, 5, 6, 7, 8, 9, 10, 11, 12. And I have a feeling, and 13. So this will contribute as Q to the 13. Okay. Now I was saying that there was deletion and contraction formulas. Many of the results that we are proving are coming from having deletion contraction formulas. So if I have a partition and I take a corner box, then I can just delete the box, and that is deletion, or I can delete both the row and the column where this box is, and I'm going to call that contraction. So what happens is that the Qrooks have a very nice formula, this one over here, for the when I'm deleting and contracting a box. Now, if I denote as H tilde, the ones that were coming from the formula, like the statistics that we did not use, they have this formula over here. This was actually proven by Dyck with the wrong statistic. So there is, I haven't been able to figure out when, but when we are doing experiments using his statistics, he's not getting this, well, he's getting this, but this one is not the one that is satisfied by the the Q-hit numbers that we have. So we were able to find computationally one, and it's a conjecture. We haven't been able to prove it, and this deletion and contraction. Now there is another deletion contraction formula for the H till the regular H for what would be hours. And that one is just translating this one, like translate using the formula from H tilde to H. So there is a way of obtaining another one, not this one, another one using the one that we have over here, and the formula to change from one to another. Now that was the point where we realized that the two versions of the Q-hit numbers were not the same, because we thought that we could get this one just by specializing the one that we have from the Qrooks, and that's when we realized that we were getting a different one. So it was kind of like a very messy situation in the sense of not understanding why things were not working the way we wanted, and why when we were doing computations, depending on what we were using, we were getting different ones. But what was our initial goal in the paper was that actually White-Paquette has a non-privileged identity for involving Q-hit numbers. So what we are doing here, we're considering a partition inside a board, and I'm looking at the graph associated to the partition. And if I'm looking at like a rectangles, if I'm looking at partitions that are given by rectangles, then the coefficients in this case are going to be a normalized version of the Q-hit numbers in the rectangular case. So Mathieu White-Paquette, he had this on some notes that he had shared with Alejandro at some point long ago. So we were looking at this identity, and we were thinking that we should be able to prove it using Qrook theory and Q-hit theory. His proof is based on, it's a very algebraic proof. Is based on the fact that he's looking at some spaces, and it turned out like this is going to be the basis. These are going to be the coefficients for a dual basis. So his result is not actually working with the Q-hit numbers. It's just saying actually the Q-hit numbers are going to be the dual basis for the basis that I'm having. And as a consequence, they are going to appear as the coefficients in this description. When we were working on this, Abru-Negro published another paper that was actually also using Q-hit numbers. In this case, they were using Q-hit numbers for rectangular, for a square shape. So although I have that my board is in, that my partition is inside this board, I'm looking at these Q-hit numbers in a way larger board. So I'm looking at an m plus n minus k board, or in this case, minus j minus 1. So what they said was that if I'm looking at the elementary bases, the coefficients are given by Q-hit numbers up to some other factors involved. So we were very curious on knowing, like, first of all, where this one is coming from in the Q-hit numbers world, and if these two were actually equivalent, if there was a way of proving one from the other. And that's what we did. So,
wait, now doesn't that prove the Shiroshian wax conjecture for
the abelian?
For the abelian case?
Yes.
Okay.
But that was also done by Cho and Hugh using p-tableaus, and by Megumi and Martha using Heisenberg varieties. So, so what we did was giving a new proof for the White-Paquette's identity using Qrook theory and Q-hit theory. We really hope that he published his proof at some point. We also saw that they were like White-Paquette's and Abru-Negro identities were actually equivalent. And then on the way, and I'm going to try to give you an idea of that in the next 5 minutes, we also have to prove a lot of relation for Q-hit numbers. And we also found like there were also many problems that we were not able to solve. and that I think that are very cool to look at still, and way more combinatorial than our results. So what I want to do here is I want to show you with an example what is the Y packets identity. So I'm taking a board that is 2 times 1, 2,1. So I'm getting this partition inside at 2 times 3. And what I have to do, I have to put, so remember that I have this K here. This K is gonna be 0, 1, or 2. So I'm gonna have K equals to 0. Well, actually, let me put it here. This is K equals to 0. This is K equals to 1, and this is K equals to 2. And what I have to do is that this, the 0 means that none of them are inside. Here, only one of them has to be inside the lambda, and here both of them has to be inside lambda. So for instance, if I don't want any of them to be inside lambda, then I only have a possible way of putting them. I have to put 1 here and 1 here. If I want both of them to be inside, then I have to put both of them here. And then the other 4 in the middle, I'm gonna have just 1. So I can have 1 here and here, 1 here and here, or I can have it only 1 here, and then I'm forced to have the other one here. Or if I have it here, then I'm forced to have the other one here. And now we do our attacking rule. So what I have in this case is, let's see, I'm doing south and east. So south, and then east up to the partition. So I'm having this one and this one. So this is Q to the 0. This one over here is south and south up to the partition, up to the partition. So if I just do this for all of them, so I'm gonna have here, I have 1, here I have 2, another 2, and another 1. So I have 2 times Q plus 2 times Q squared. And in this one, I have 3. So I have Q to the Q. And now I also wanted to put here down what is the partition associated to the shape here. So when I'm gonna have, like in this case, M is 3. So I have 3 to the 0, 3 to the 1, and 3 to the 2. So what this is saying is that I'm getting the factor from here, but then I'm gonna have 1 times x 3 to the 0 of xq plus 2q plus 2q squared x 3 to the 1 xq plus q cubed x 3 to the 2 xq. So they are kind of like in my mind, I have first the partition for the lambda, like the lambda for the q hit, and then I have the shape for the chromatic polynomial. So I have this game between the two different ones. Now, I don't have much time, but I want to give you some idea of where our proof was coming from. So our first step was to go from chromatic symmetric functions into polynomials. So we were just like, you just take an M that is large enough, and then you can just look at the similar identity. Instead of having symmetric functions, we have now polynomials. And we were denoting by this, when I'm having M colors or M variables, lambda is my shape, and N is gonna be the largest rectangle that I'm considering. Now, one of the properties, like the reason why we decided to do this was because actually by looking at the degree of xm, we have a very nice thing. What happens is that the degree of x to the xm, of the degree of any variable, is at most 2. And this is coming because of the shape that I'm considering here. So what happens when I have the DICKPATH with like the abelian DICKPATH is that I can look at this first triangle and this second one, and those are cliques, which means that all the vertices are connected, because I can go from each of these vertices to each of the other ones here. They all have to have different colors. And the same happens in this other part. So I have 2 clicks. And then in this other part over here, I'm going to have actually a bipartite graph, which means that if I'm looking at the colors, for each of the colors, I can have at most 2 vertices with that color, which means that the powers of x to the m are going to be 0, 1, or 2. So once I'm in the polynomial case, I can just look and say, okay, I'm going to look to the largest variable, and I'm going to look at the coefficients for each of the degrees that I have. So what we did was taking my polynomial in m variables, and I split it into what happens and how it's affected by the different colors. So I can have that there is no vertex with color m. So I'm just going to have the same chromatic polynomials with 1 color less. If I have 1 vertex, then we identify where was the vertex, and when we describe it by using the chromatic polynomial, where I'm going to define this in a moment, but I'm using m 1 color less. Here I'm counting how it's affecting to the powers of Q. I'm kind of like controlling what is happening. And the same when I have that the color M appears twice. So the notation that I have over here, if I'm just having I and J, what I'm doing, I'm removing both the column and the row of the box. And in this other case, what happens is that I'm going to have to remove a column or a row depending on the value of I. So what I'm doing here is I'm first removing columns, and then I'm removing rows. Columns from left to right and rows from bottom to top. So this is basically kind of like figuring out what it means to have only 1 color of one color M, and figure out, depending on which vertex it is, how it's contributing with the Q. So it's kind of like very controlled way. And we were able to do it because like we kind of like only have 3 terms to look at. And the other thing we did was put in the Y-packet's identity in the polynomial version. And what I want to do now is I want to compare these 2 expressions. So what we can do is we can apply induction as much as possible, because all the terms that appear here are going to be now smaller in some sense, smaller on the size of, on the number of colors, the size of the board, and things like that. So I can actually simplify, like apply the induction and simplify. And the next thing was looking at comparing the coefficients of these 4, I'm going to call them monomials. They are not monomials, but I'm taking them as if they were. And then we are matching coefficients. So what happened is that this is the one corresponding to x to the 0, and these were matching directly. Now we were having 2 terms for xm and 1 term for xm squared. So from there, what we were able to do was getting this linear and quadratic, these 3 relations between Q-hit numbers. They look awful. And we tried to prove them using bijection. So we tried, like, if I have, for instance, here, if I have a Q hit, like here I have a Q hit. So if I have a rook placement, can I associate a rook placement in this other side with some power and control the Qs? And the answer was not. So the way that we did this was, I can use now the relation between the Q hits and the Qrooks. So what we did was translating this into Qrook identities. I decided not to put them because they were very ugly in some sense. You had enough with the other ones. And then prove these Qrook identities using generating functions techniques. So this was very tedious in the sense of they were not that as combinatorial as we will have like. And then we were wondering to the other question, if these 2 identities, the Y packets and Abru Negro, if they were equivalent, and we were able to solve that using same techniques. The idea was assume one of them. Then we prove the other one for rectangles. And once you have it for rectangles, it follows for any other shape. And to solve the ones for rectangles, we were using induction and relations of Q-hit numbers. So that's why like we were getting a lot of relations for Q-hit numbers, more coming from the sense of we know that these two identities are true. So if we are reducing it this way, we are getting this relation, the relation should be true. And then we were proving the relation. So that's kind of like how we were getting that many relations for the Q-hit numbers and kind of like pushing that side of the project. To have an idea, for instance, like if I look at Abru-Negro identity, assuming that white packet is true, then doing it for rectangles gave us these two relations, which initially was not very, I don't know what I would get this if I were to do it in any other way. This is relating Q-hit numbers in very big rectangles, square boards, and this in terms of smaller rectangle shapes. So I don't really know how we will be able to get this kind of relations. And in this particular case, especially in this one, there is a very nice, we were able to prove it with a deletion contraction relation that was very nice to do. At least it looked more combinatorial than other proofs, especially those with generating functions. And just to finish in the last minute, I wanted to talk about the cool problems that we found on the way. And it's actually the fact that we are missing many proofs and that the proofs that we have are not as fulfilling as one would think, especially because we would like to have bijective proofs. So for instance, white packet's identity is giving a relation between colorings and rook placement. Is there a way of actually going directly from the colorings into the rook placements? Can we do that? And the other one was the one done by Chohu and Abru-Negro. They are both doing E expansions, and one of them is using P tableaus and the other one is using Q-hit numbers. Can we give a bijective proof to go from one to the other and the other way around? So these are kind of like things that we haven't, like we really didn't know. I have to say that our first approach to many of the identities were try to do it more combinatorially in the sense of bijective, but we weren't able to do that. And we also found other Q-hit relations that we were proving and identities that we were proving using the generating function and other approaches, but we haven't been able to do it with bijective proofs that we thought were very interesting. And I think that's all I have.
Awesome. Let's thank the speaker. All right, if you have any questions, feel free to unmute yourself and you can go ahead and ask. And Laura, I muted you as well, so you have
Yes,
to.
yes,
Oh, you already did. Okay, cool.
Otherwise, we don't hear his sound effect.
Yeah, no, but it was a nice sound effect.
We try. All right, are there any questions? Feel free to ask in chat if you don't want to unmute, but if not, you can unmute and go ahead.
I'll ask. Have you looked at the replacement Q goes to 1 minus Q? And I ask because you're working with an E positive expression. And I know Greta had actually looked at this for the reverse one. If you start with a short positive Q expression and replace Q goes to 1 plus Q, you get E positive expressions sometimes. And so the reverse question would be also interesting to know. If you start with an E positive expression and you go Q goes to 1 minus Q.
So we have looked at that, but for another part. So we were also looking at the operators that there are some results for the Q chromatic symmetric function using the operators related to the nabla and those things. That there have been like some, we were looking at that, but we haven't looked for that here. Let me take a note.
I would be interested to know if something like that works, just because it's a weird phenomenon that I'm not sure has been explored much. And I know Greta had looked at it though, so that's one of the reasons why I asked.
He hasn't mentioned anything, but I would also say that at some point it became that we kind of like wanted to wrap up with everything that we had, because it was so dense on the identities and the arguments were just like kind of like keep pushing them up to the point when you're getting something that is in Q numbers and then you just have that is true. So there are many things that we haven't had like the time to explore and say, okay, now what can we do with this? That is actually not just pushing Q identities.
Okay, let me ask me another one of those weird questions. Have you looked at what happened when you put root of unity? It's linked with our last algebra meeting where we talked about the cyclic sieving phenomena. So are those Q functions satisfy any cyclic sieving phenomena? So the first one is to put -1. So with coloring, when you put -1, often you get acyclic stuff.
Yeah.
And so on. So I wonder here, what happened when we put root of unity?
We haven't checked. So that will be some more specializations to do.
Yeah. Yeah.
But no, I don't know. We haven't tried anything apart from that. And it all started because Alejandro wanted a proof for white packet's identity using Q hits.
Okay, I will call you Laura. It's gay packet.
I call him Mathieu, and that's
Gay packet.
But yeah, then like this thing of figuring out that the Q hits were actually different came up like during Christmas. And then we realized that half of the things that we had were done with one version and the other half with the other version. And yeah, I think that then tell what happens like when you figure out that something was not the way you were told. And it was very fun because Hagland actually has one version that he claims is the same that Dworky. And he said, like, we contacted him and we said, hey, like the way that you both put it on paper is actually not the same. And he was like, well, he just told me during a conference. So I just used the one that he told me during the conference. We were like, yeah, but it's not the same. So yeah. And then I'm also gonna take notes of Adam's question about all possible directions.
Well, for other direction, it might not. You might not want to consider cylindrical, but spherical, or cylindrical in the other way.
Yeah, I mean that's what when I say before, like there are not much of the Q-hit theory that is developed. Like Alejandro and Joel kind of like developed it to non-square shapes, and that was all that had been done. So in this sense, I think the project is pushing more into the relations of Q-hit numbers. And
yes.
Are there any other questions? If not, let's thank the speaker again. In a second.